because I was sick, I didn't want to get hot drink. I was going to get a cafe latte originally, but then I was like, oh, what's a cafe Coke? And they were like, it's basically just a little more chocolate. I was like, I'll get a cafe mocha. And everything's in the cafe mocha. So it just lasts longer for the same price. Fair. At first I hated the coffee flavor, but got addicted to it. So now it just tastes like chocolate and it's healthier than most chocolate. This is cheaper.
Okay, cool.
Considering yes, considering I can see.
Okay. Welcome back. Hopefully weekend, at least a time to take some break. It sounds like it's midterm season though, at least the first round. Then you get midterms every week for the next 4 weeks, maybe 6 weeks, and then at some point, I don't know. Exams, yeah, it's like exam season. Yeah. At one point I tried that structure of like have 3 midterms, but I felt like every time I turned around, I'm like, oh, I'm prepping and grading another midterm. It's like, it was not worth it. And I couldn't tell if anyone actually learned anything by the end. They were just...
They've been cooled down for so long.
Yeah, it's hard.
It takes the first 70 or 60 in an exam to like the fire under most people's bellies.
Yep.
Where they're like, okay, now I have to focus in.
But here, so there's no exams for our class. We have projects, we have homeworks, we have quizzes that we'll build together. They're all kind of similar to quiz 1, where we took a class, talked about it, figured out what are we doing. The other logistical thing that I wanted to talk about was like late submissions are total. There are no late penalties. The only thing that I ask is that if it's going to be late and you need extra time, like submit a note on Husky CT. There are mistakes of like, oh, I thought I clicked submit, but it's actually saved. Like that's an IT issue and it's not a problem. Like you don't need an excuse of like, I clicked the wrong button. It's okay, I trust you. I think, I assume you did it. But anyway, so the main thing, if assignments are going to be late, put a note in Husky CT that says, hey, I need whatever. If it's an extra 24 hours, no problem. If it's an extra like 5 days, yeah, that's okay. And then the other part is, do you need help on the assignment? Like, how are you getting help? So are you coming to class? Do you have questions? Do you want to stay after class, or do you want to set up an appointment with me or one of the TAs? So those are the 2 things that I need to know. Is 1, when are you getting it done? And then 2, what do you need to get it done? Time is fine. Like, just extra time, that's pretty easy, but it's okay. Any like questions about that? Okay, yeah. Yeah, and so like if you want to send me an email, it's fine, but the main thing is like also on Husky CT, if you submit something in that assignment, TA knows as well. Cool. All right, so here we are in Module 2, Constrained Dynamic Motion. And I mentioned this like as we were kind of taking a tour of the class. A lot of times this is not the second thing you do in dynamics. This is usually left to the very end of the semester when everyone's rushing and they're forgetting everything that gets said. So I like to put it right up front because it's all like geometry and constraints and all this like cool stuff that we can use in all parts of dynamics and engineering. So let's jump right into homework. Copy this, paste it in, and do I want to grab a screen grab? Get the constants in there, right? Okay, Do you know what a flywheel is? Have you heard that term before? No? So if you've heard of what does a flywheel do? Keeps momentum, okay. I ran into some students that have like a circuits exam today or tomorrow or something, and they were kind of stressed about it. And but circuits is all like mass spring dampers. It's the exact same math. There is no difference between RLC circuits and spring mass damper setups. At least abstractly, the math that used to solve everything is exactly the same math. So, is a flywheel a resistor, an inductor, or a capacitor? If you're making like a circuit with springs, masses, and dampers, what would your flywheel be? Capacitor? That's a good guess. Like storing something? Say no. Inductor? Why inductor? Okay. Yeah, so capacitors would be like a spring. Like if we had a torsion spring on a spinning mass, we would have one capacitor is sort of like storing up energy, then releasing it, then storing, then releasing. That would be our torsion spring, the capacitor. The flywheel itself is like an inductor, so it keeps the motion going. It always helps to take a guess, right? And so actually there's some great scientific, like if you're into like the science of learning, if you make a wrong guess and you get corrected, if it's something that you think about, you'll remember that for the rest of your life. If you already knew the answer and you just kind of said like, got it right, like you confirm your own bias, a lot of times those lessons get forgotten. But if you correct it. So anyway, we have this like inductor kind of flywheel. It can store energy. This is great we use it in like automotive engines and all sorts of stuff. Like the pistons need to keep moving even though they're not always delivering energy into our engine. So we use a flywheel to maintain there's always that rotational kinetic energy, and it keeps the whole system rotating. Same like lawnmowers. This is kind of like a lawnmower start. We have two forces applied. We know how fast this thing is going to accelerate. So I want to know what are the forces that created that acceleration. And I'll leave it at that. I want to see what you think about this to start. I'll zoom in a little so we can kind of see. So I just want to see where you want to get started.
It doesn't feel like it was made any easier for us. Oh, you feel like you hold it this way, rotate. But it didn't Or sorry, it's gonna be
Yeah, and so we're told that it's negative 50 radians per second.
yeah.
Radians per second squared.
Oh, so it's negative. So it is.
No,
Oh,
so
it's the number actually.
yeah.
I mean, that makes a lot more sense.
Yeah, so it's just.
I know I'm not gonna do this terribly, but I need to start this week if I want to prep for the exams. But I'm curious to. It's so he said anywhere from Sunday to Saturday.
Yeah,
If they're the same value, like do they cancel? Possibly.
Okay.
I think that they don't cancel the syllabus. I know we have. Yeah. I thought it would be this one and then this, either the Tuesday, Wednesday, Thursday. Probably not Tuesday. Probably not Wednesday. So we do. Yeah, I'm not sure if it's fair. I feel like it would still be one in my head.
I have a feeling of being.
Yeah.
That's not.
No, my goal is to be.
Yeah.
Fatal flaw of undermining and running the class, forgetting how seriously they take themselves. Exactly. Torque. No, not torque. Tangential, centrifugal force. That's Chris. He said it'd be here. Chris, I know you're in the YouTube, Chris. Focus up, Chris. Jimmy, tell my buddy Chris how late he is to class. Chris should get a streak.
Yeah, so usually
Jimmy, what Pokemon is that? Is it Mudkip?
you want to access things and store as much kinetic energy as you can. In old school, we used to store fire engines. Old school ones, flywheel, it's like a 5-foot diameter.
How does it list out the
Concrete block. Once it starts spinning, it's nothing. Stop it.
Oh, wait, it's but it's in the k-axis. So it's moving k points upwards out of the diagram towards us. So it should rotate this way. If it's negative, it rotates clockwise. It's facing out. If it was positive, it would be face wide off. If it's negative, k points out upwards out of the diagram. Negative k points inwards into the diagram. So that is clockwise. I was going to two. It goes on that.
Just maybe torque. Yeah, shoot on torque, right?
You could equate them. Okay, I see. That's not good. So we have our mass, we have our radius, and then so what is F? If F is our given radius, what are the equations that we know?
All right, so here's like questions that I've heard so far for like trying to get us started. Is all right. We know moment of inertia. So the first question is like, what is moment of inertia? Like if someone says, well, I just told you, our moment of inertia is 0.5 kilogram times meters squared. What information did that just give you? Other than it's less than 1, but more than 0. I mean, there's like Yeah. Yeah, so moment of inertia and moment, they're definitely like directly connected to each other. Like Newton's second law specifically says, like the amount of force that you need to accelerate an object is proportional to mass. How does that relate to our moment of inertia? Is there a similar rule for moment of inertia? No. Objection, you're leading the class, you're leading the witness. I am leading you to try to see. So moment of inertia is a resistance to like twisting motion. So the bigger the moment of inertia, the harder it is to spin something. That's what it's telling us. So 1/2 is easier to rotate than 20. That's like, now it's 20. I should have picked a better number. 20 times, or 20 times 2. So 40 times harder to rotate than 20 kilogram. Ooh, love that one. So someone just wrote in, sum of the moments is I alpha. Where like alpha is our rotational acceleration, moment is like total moment on the system. All right, so that was the first part. Next question that was coming up, trying to figure out. Well, first there was like a kinematics kind of problem of, look, the forces are twisting in a clockwise motion, and yet acceleration is designated as a counterclockwise motion. And then there's a whole negative sign in that alpha term, the radian, it should be radian per second squared. So what in the hell is going on with our diagram here? Like, why is there a clockwise, a counterclockwise, and a negative sign? I'm going to scroll over to. All right, we have, oh, yeah. Counterclockwise is negative. So when we have, yeah, exactly. So we have our x-axis this way, y-axis kind of straight up. Z-axis comes out of the page, out towards us. So right-hand rule says positive, everything positive. And this is, and again, dynamics, it starts to matter about which direction you call positive, which one you call negative. In this case, you could probably figure it out because you'll get a negative force and you'll be like, oh, it's probably positive, and then flip it around. So sometimes it doesn't matter. In this case, it kind of does. So what we're saying is that this is a positive, what's drawn on here is a positive alpha, but we have a negative acceleration. So that one's kind of like kinematics, quick intro to rotation. And then then the next thing that came up was, what is our sum of the moments? We have two forces, yeah. Force times radius, yeah. So force times radius, yeah. And we got two of them. So is it double? So the question that came up was like, do we have 2 times force times radius? Do we have, because there's also like that idea of the moment couple, right? F times D, just force times distance, 2 forces, 1 distance. What do we think? Which one? There are 2 chords, yeah. 2 chords, both applying F. Oh, sorry, we'll go back and then front, work our way forward.
Because they're both going in the same direction, you can just pick one that's bigger behind the two, and just go back.
Okay. As far as the moment is concerned, right? Yeah. And then some kind of
They have to be equal forces for it to have a constant motion, so we could treat them as one,
okay.
since they would be the same volume.
Yeah. If I add the right vector to the left vector, just move them, put them on top of each other. What's f plus negative f? 0. But opposite. Okay. All right, so then let's have our moment then. All right, this one's a side project. It's not directly the homework problem, but if I have a force applied at a position, what is the moment applied around that point A? Because it's different, right? Like the moment applied, if I call this like point B, the moment around B is 0 because I'm applying the force at B. But the moment around A should be something non-zero, right? Like a wrench, the bigger the wrench, the more torque you have. So what is, yeah? 2 by 2J? 2 by 2J. Why is that?
Because you got 2I,
Yeah.
2J, which is the 3 plus the 1.
Yeah. 2. So why is it 2? Oh, for 4? So this one is like meters. Like describing the position of B. Yeah. Okay, yeah, like 3 times 2, something like that. Where is that coming from? Like what, do you remember like the first R cross F? All right, thanks Jimmy, nice. So it's always like force times, we always need a force and a distance to describe torque and moment. Torque is kind of like the magnitude of moment. Moment is the vector describing like twisting forces. So I would say 2I plus 1J crossed by negative 3J. And this is going to be a Newton meter. So 2 times negative 3, what's that? That one's not a trick question. 2 times negative 3. Negative 6. All right, so we got negative 6 I cross J. 1 times negative 3. Negative 3. J cross J. A 0? Yeah, which one's 0?
3, because the 2J just went to 0.
J cross J. So if you take a vector and try to find cross product of itself, it's 0. Cross product.
And the I and J are in sequence, so they become K.
They become K. So this is a 0. This one becomes a K. So the moment about A is negative 6 K Newton meters. Is that telling us that it's clockwise or counterclockwise? A negative 6 Newton meter torque. Clockwise, counterclockwise? Clockwise? Yeah, so into the page, clockwise, negative. Have you seen like the visualization of a cross product before? Have you seen? No. So like if you have two vectors and you take the cross product, it's as if you made a parallelogram out of them and found the area. So really when we're talking about torque, we're saying like what is the area created by distance and force. So that's why if you take the cross product of a vector with itself, like A cross A or I cross I, there's no area created by a line on top of itself. So no area, no torque. All right, so that was our moment. I hope you enjoyed. I'm proud of you. So now we have a few extra tools, right? And then we spent so long doing free body diagrams, but I didn't see anybody like really put down free body diagram. Do you think it would help in this case? I didn't see anybody commit to it. If like, this is my new free body diagram. Do you think it would help? Do you want to do that exercise? I think it would help. We don't have to. If you're like, no, the answer has come to me. Like I've been touched. Now I know. What do you think? Free body? All right. Try it out. Can we assume it's a point mass? Why not? It would what? Forces would all cancel, yeah. Point mass assumes that that rotation is kind of irrelevant. Not that it doesn't rotate, but just it's not part of the calculation. So we need a rigid body, so we need something. What are the forces there?
Virginia code all the time. Maybe drop another class for it. This is my fault. This is no, I'm not. If I spend it, because I know they do it for me. To keep track of it. The seats are too close together. I feel like if I jump from the highest area into the wall.
So are these the only forces we need? Like F, a positive F, a negative F? Some people had the idea of like maybe put both F's up top, call it like 2F, and now you have one vector. So the only other thing, there are like reaction forces because we are constraining motion. Like a flywheel, the assumption is it's not, if you pull on it, it's not going to start moving away from you or moving towards you. So the only other thing that I would say is like we do have some kind of Rx, some kind of Ry. Like if you put a bearing in there and say you have to rotate around this bearing, there's got to be something. There's got to be some kind of constraint force there to keep you in that one spot. So then, so people were kind of working on this, thinking about it, but then trying to figure out, like, what do I do with MAX? Is there an MAY? Like, what are these? How much acceleration do I have here in terms of like A, the change in velocity? How much velocity change do I have? Not rotational, but actual like motion. 0, some 0. And even from like our free body diagram, we have a positive F and a negative F, opposite direction, so acceleration is 0. There's no forward, backward motion. There's no up, down motion. There's not even forces applied there. So these are 0. So what's that I alpha? How does that play into our kinetic diagram? Well, really, it's the same as like writing in, here's my MA vector. Like this is my change in momentum. We can say this is my change in angular momentum. So here, this is going to be my I alpha of saying like, these are the forces applied, those forces create torque, and they're all leading to like some I alpha rotation, kind of like that. And now I've got my moment all over our work. So let's take all this. Bring it down here. Now it's the same process as statics of like we have forces in the X, we have forces in the Y, we have moments, sum them all up, set them equal to motion. So in my X, I have F minus F equals 0. Not very helpful. It's just saying that it's equal opposite. Y, I have Ry. I guess I could add a plus Rx equals 0. In the Ry, I know there's, oh, sorry, go ahead.
I know in a lot of our other classes we put the moment in our free body diagram. Should we include that in the free body diagram or the kinetic diagram?
So if there's an actual like moment applied, like not, so a point moment, not forces creating a moment, then you can do either or just don't do both. Like the way that I drew this free body diagram was just forces that are applied, but I could have said these two forces are creating a couple, so there's those two forces are gone. I'm gonna draw a moment instead. So yeah, either way, but as long as you don't do it both. Similar reasoning for like centripetal acceleration and centrifugal force. You can do either or, but don't do both. Don't put both of them in your diagrams. Okay, so now we have some of the moments. What is the moment created by, let's highlight it. Can I highlight? Must be able to, right? All right, let's do this. What is the moment created by F star? Just that top F. How much torque is it applying? F times R, yeah. Which direction? Is it clockwise or counterclockwise? Clockwise, sorry, clockwise, thank you. Clockwise. So a negative R F, that's our star. How about for F block? Just so we have two different symbols. What's F block? Same thing. It's still R, so it's applied at radius R. It's perpendicular to it, so moment arm is R. And it's still in the same like torque direction, twisting direction. And then I can say it's all equal to I alpha. Now, I mean, this was like a long conversation for a very short equation, but that's okay. Now we can do it however we want. Negative 2 RF equals I alpha. So we kind of, and this is a good way. You can do this for any problem. Where if you know what forces are applied, just draw those forces, figure out what the moment arms are, add up all the moments, set them equal to rotation, like I times alpha, and that'll tell you how much acceleration you have. Oh, so clockwise, counterclockwise. This is positive. This is negative. Because if I look at X, Y, Z, right-hand rule says positive rotation is around the z-axis, counterclockwise around the z-axis. And that's why I'm like sticking to that negative and negative, and keeping track of kinematics, like how we're defining everything. Cool. And if someone else had kind of plugged this in, they got like 125 newtons. How does that sound? For F. F is 125. What do we think? Does F equal 125? Yep. So it's some 2 so far. Bless? 2125. Okay, cool. Bless you. All right, we're not going to go through the whole problem right now, but this is like, so general mechanism like this is called a slider crank, or like piston slider or something like that, where we have this roller can move left and right. You can move wherever it wants to, but it has to be connected through this link 2 to link 1, and this one is fixed. So over here, and I like to label it, call it O, A, and B. So B can move left and right, A can move in a circle around O, or at least a semicircle, and then O is not allowed to move. That's our kind of system here. And it's not going to fall off. There's no cliff. It's not going to fall. It's meant to just show you that that is the flat surface that it has to move along. So we have a force pointing down. So let me like draw this out. More like this. So it always creates some kind of triangle. The first question to just kind of think about, and then we'll get to it, we'll get back to it next time, is what kind of triangle would you make so that R is 0? When is that like reaction? So sometimes it's positive, sometimes you have to pull on it, sometimes you have to push on it. But when would R be 0? Like at what point does that happen? And this kind of analysis where and what we're doing is imagining that the thing is moving, but the change in momentum is 0 somehow. Either the links themselves are very light, and then we don't have to worry about rotational inertia, or things are moving slowly. And that analysis is called quasi-static. That's the fancy way of saying, like, I didn't feel like doing dynamics today, I'm doing a quasi-static analysis. So I'm doing statics, I'm allowing motion, but I'm not allowing momentum to change. So this is a great vocab word when someone's giving you a hard time. Like, did you consider the dynamics of this? It's like, yes, I did. I considered it quasi-static. Get off my back. So what do we think? In our quasi-static analysis, which means it is static, it's just moving, what triangle would make R equals 0? Or what configuration? What angles do we need?
R is a reactive force.
R is some kind of reaction force. F is like 100 Newton. We'll say that it's always 100 Newtons. I forget if it's 100 or 10, but either way, at some point it goes to 0.